with the webinar session. To begin with, we have Mr. Abin Varghese. He's a fourth-year PhD student at the IITB Monash Research Academy. He has completed his integrated master's in physics from IIT Trivandrum. Thereafter, he joined the IITB Monash Research Academy for doctoral studies. He's working with Professor Saurabh Lodha in the Electrical Engineering Department at IIT Bombay and Professor Nikhil Medhekar in the Material Science and Engineering Department at Monash. He's currently at Monash and his research is on exploring two-dimensional van der Waals heterostructures for optoelectronic studies through experimental as well as first principles-based DFT calculation. So Abin is here to take us on a journey to explore the light. Now over to Abin.
Hello everyone. Good afternoon, and I hope I'm audible.
Yes, Abin, we can continue.
Okay, thank you. Thank you for the opportunity to talk. I'll share my screen right now and probably switching off the video would be better. So good afternoon everyone again, and my talk is on the introduction to optics and photonics, and I thank the IIIB Monash student chapter at IIT Bombay for the opportunity to give this talk. I'm a PhD student in the IITB Monash Research Academy and working with Professor Saurabh Lodha in the Electrical Engineering Department at IIT Bombay. So to start off with the talk, and this talk is all going to be about light and what has happened to light and what we can do with light. So the outline of my talk is as follows. I'll talk about the lead up to photonics and how it's different from optics. And then I'll move on to some photonic devices, just preliminary understanding of those devices. And then the important aspect of photonics in our daily life. And what is the research being carried out in photonics? In terms of silicon photonics and some new materials which have come about in photonics, which are the two-dimensional materials. And then about this important aspect of what photonics can do during this COVID-19 pandemic. So to begin with, how did photonics come about? So what we know is that the ancient Greeks had some idea of geometrical optics, and they even knew about ray optics and how light interacts with some things like mirrors. By the 12th century, the invention of the lens happened, and in the 17th century, Snell's law of refraction came about, and Fermat's principle, which talks about the fact that light takes the path which has the least time. All this while, people had no clue what exactly the nature of light is. And in the 17th century, these two gentlemen, Newton and Huygens, had their theories. Newton had his corpuscular theory, and Huygens had his wave principle, both of which could explain certain observations relating to light. And in the 18th and 19th centuries, the phenomena of diffraction could be explained using the wave principle, and also Maxwell's laws of electromagnetism came about. But in the 20th century, Albert Einstein came and said all this is wrong, and light actually has a dual nature, meaning it can exist as both particles and waves, and these tiny packets of energy in which light exists are called quanta, and that came to be the quantum theory of light. And in the 20th century, the mid of the 20th century, with the development of this thing called maser, which is microwave amplification for stimulated emission of radiation in 1954 by these two gentlemen here, began this exploration into several other photonic devices. That's where we get the word photonic, which comes from photons plus electronics. So what's different in photonics than in optics? So as was mentioned earlier, what is photonics? Photonics is the generation and harnessing of light and other forms of radiant energy whose quantum unit is the photon. So photonics would deal with all kinds of radiation, right, from the terahertz to the UV to the IR and so on. And how does it work in photonics? It works with the generation, detection, and managing light. And how does that happen? As this cartoon shows, it happens through all these processes, which are transmission, emission, signal processing, and so on. And the history of photonics, which I'll take up from the previous slide, in the 1950s with the masers, then came the lasers and optical fibers, which are analogous to the copper wires that transmit electricity, and in the sense of transmitting light from source to destination. And with that came the era of optical data communication, and the 2000s and onwards have spurred this interest in the Internet of Things based application, which aims at connecting different sensors uh, to the internet so that data can be accessed from different places quite easily. So why do we want to study photonics? We want to study photonics electricity. So photonic circuits, if at all there are, could be faster at transmitting information from one place to the other in comparison to electricity. And because in photonics we use all frequencies of radiation, we can pack more information, and more information can be processed or transmitted in comparison to electronics. And in terms of the energy efficiency, to process 1 bit of data in electronics requires 1 picojoule of energy, whereas that in photonics requires 1 femtojoule. So in terms of energy also, it is quite efficient, and that's why photonics. And with all this talk about quantum and optics, so what is photonics? Quantum optics? Well, I'll leave it to the audience to figure that out. Moving on to photonic devices. I'll talk briefly about a few devices which have caused this increasing research in photonics and has made a lot of the applications which I'll talk about in the coming slides possible. The first of these devices are the photodetectors, which can detect light at different optical powers. They're used for sensing light, and by architecture, these devices could be something like PN junctions. They could be phototransistors or Schottky diodes, which are metal semiconductor junctions. And these photodetectors work on a spectral range. That is, they sense the radiation within the spectral range for which they can function. And there are other important parameters like responsivity and detectivity. Detectivity would be the minimum power that the photo detector can sense for a given radiation. Next are the light emitting diodes, which everybody knows is a device which emits light, and it does so by this process of carrier recombination. This is also a PN junction, but the difference from photodetectors is that an LED is a forward biased PN junction, and a photodetector is typically a reverse biased PN junction. So the forward bias allows the carriers to recombine when a current flows, and they are in all sorts of wavelengths, right, from UV to IR, and they're used for a lot of applications. Next are the lasers, which also are light emitting devices, but they emit light by a completely different phenomena, which is called the stimulated emission, and hence laser, which stands for light amplification through stimulated emission of radiation. And it has a gain medium which is inside an optical cavity and which is pumped, and that causes the emission of radiation. So the lasers are typically known for their precise wavelength at which they emit, and lasers come in all sorts of powers, like from high powered lasers, pulsed lasers, femtosecond lasers, and so on. And next are the optical fibers, which carry light from source to destination, and these are based on this phenomena called total internal reflection. They have this architecture of a core material which is made up of normally silica, and they have a cladding around it, and the total internal reflection that happens at the edge of the core and the cladding gives rise to this transmission of light from one place to the other in an optical fiber. So moving on to photonics in daily life, where all these different devices are employed. So the 20th century, we know, was the century of the electron. A lot of electronic devices came about, whereas the 21st century, we can rightly say, is the century of the photon, and I will show you examples of that. First, in case of communication, we switched from communication using a landline to something like optical fiber-based communication. The second is in the field of entertainment, where we moved on from the diaphragm-based gramophone systems to something like the compact discs, the DVDs, and the Blu-ray discs, which are very common nowadays. In case of displays, we moved from the CRT displays to the OLEDs, which are light-emitting diodes, and the TFT displays. The incandescent lights, which used a filament, have been replaced by this LED-based light bulbs, which are far more energy efficient. And life sciences and health have taken over endoscopic surgeries, which employ photonic methodologies. And in terms of manufacturing, and the old drilling and cutting using power tools has been replaced by far more precise laser employed drilling and cutting technology. And in addition to all of these, what's new? What's new are the flexible devices and wearable biosensors, which are only possible because of this revolution in photonics. To add to that, healthcare is a major sector which has seen a lot of photonic devices that are being employed. And MRI, as we know, magnetic resonance imaging, uses a lot of photonic, is a demonstration of photonic devices, and even optical endoscopy and laser surgery. For advanced microscopy, a lot of acousto-optic elements are employed, and we have all heard of laser treatments in eye-related ophthalmology and in hair and tattoo removal and so on. Another field where photonics has not been very commonly discussed is in the pulse oximeter, which is a device that senses the oxygen concentration in the blood, and that makes use of LEDs for that. Even DNA sequencing employs photonic devices. So moving on to manufacturing, we are all used to the barcode, which is a ubiquitous thing that comes up everywhere in our shopping requirements. And it's an example of a photonic system that is being used. The electronic devices that all of us use, the mobile phones and the charge coupled displays, all of them employ photonic devices. And it's also employed in solar energy harvesting and even in smart farming, where sensors are used in agro farming. We know that the optical fibers are responsible for intercontinental internet access, and the fiber optic length across the globe reaches 28,000 kilometers, which is a huge contribution of photonics. And the photonics market in 2019 amounted to around 700 billion US dollar. And as we can see, a lot of optical components and medical components, lighting and communication have played a significant role and have seen growths of over 5%. And this growth is set to increase by more than 5 to 10% in the next coming years. Talking about the research in photonics, the research is highly interdisciplinary, as can be seen from the publications which have come about in journals relating to different fields, from optics to physics to material sciences and engineering. And what are the different directions in which the research in photonics happens? The directions are towards making efficient sensors, towards integration of photonic devices with silicon technology, about which I'll discuss in the coming slides. And the research also looks at harnessing new materials and their properties for different kinds of photonic applications, and also developing lithography tools. There are a lot of specialized journals which deal with photonics. Nature has its Nature Photonics Journal, which is highly regarded as one of the best journals with a very high impact factor. And the OSA, the Optical Society of America, has journals, and even IIIB has journals specifically reserved for photonics-based research. Another interesting aspect of photonics-based research is that we can control what we do in extraterrestrial domain. Like, for example, this laser-induced breakdown spectroscopy tool has been used for elemental analysis in the Mars rover. And quantum computation uses extensively photonic technology. As we know, the qubits in quantum computation can be related to the polarization of photons. So single photon emitters are highly sought after in quantum computation. So where is the bulk of research being done in the photonic sense? I mean, in what material? So the material of choice has been silicon for a long time. And why so? because silicon has been around for a long time owing to electronics. Silicon has been synonymous with the electronic industry since the 1950s. And photonics typically employs the 3-5 semiconductors like the gallium nitride or gallium arsenide for manufacturing LEDs and lasers. But the problem is that photonic devices made of 3-5 semiconductors cannot be directly integrated with the silicon technology because both of them use different manufacturing technology. So the industry doesn't is not uh, prepared to make both the technology compatible with each other. So, is it possible that we can integrate the silicon integrated circuit technology with photonic devices? Well, it's possible, and that's the field of silicon photonics. How do we do that? We do that using the fact that the optical and the electronic components can be assembled on a single SOI chip instead of a silicon chip, where the SOI stands for silicon on insulator. The insulator is where the waveguides are typically grown in the SOI circuits, and the insulator typically is silica. And why do we need silicon photonics? We need silicon photonics because, as I had mentioned previously, light can enable faster data transfers over longer distances. And silicon photonics, the aim of it is to make the photonic technology compatible with silicon. And it is energy efficient, and we can store more information using the different frequencies of light. And this is an example of that. We can store information in different frequencies of light, thereby transmitting more information. So the overall aim is to have optical signals as well as electrical signals going into a single circuit. And Intel has done a lot of research into siliconizing photonics using different kind of photonic devices, and it has come up with this 50 Gbps silicon photonics link, which can transmit information from one chip to the other based on photonic technologies rather than electronics. The other materials which have gained a lot of attention recently are these two-dimensional materials. The first two-dimensional material was graphene, which is a two-dimensional sheet of carbon atoms. And the important thing to note is that graphene was known as the wonder material, and it got the Nobel Prize in 2009 owing to a lot of exceptional properties that it shows. It is a material with a zero band gap, which has enabled broadband photo detection from the UV to the NIR region, and it has resulted in high-speed photo switching devices. And vapor scale graphene integrated circuits have also been developed. The, the, the disadvantage of graphene when it comes to other optical applications is the band gap. So there are other two-dimensional materials like the black phosphorus or the transition metal compounds, which have band gaps ranging from zero point 0.3 eV to all the way up to 2 to 2.5 eV. So why are these materials quite prominent in research? Because these materials have high optical absorption and they are flexible. That is, for the upcoming applications in flexible electronics and biosensors, these devices play an important role. And in addition, these devices have opened up new fields of research like the valleytronics in case of the 2D materials, in which, in addition to the spin degree of freedom, the valley degree of freedom of an electron sitting in a valley of the conduction band can also be used to transmit information. With all these 2D materials that are around, it is possible to construct these 2D heterostructures because these 2D materials interact with each other via the van der Waals forces, and different materials can be stacked on one on top of each other, and they can be made to fulfill certain application requirements. Like, for example, this particular research which came out of our group recently talks about WSE to RES2 heterostructure, that is 2D materials stacked one on top of the other. And the interface gives rise to a new band gap. The band gap of both the constituent materials is above 1 eV, and the interlayer band gap is around 0.7 eV, which enables the detection of light in the infrared region. Along with that, these devices have shown high responsivity and fast photo switching, which are used for photo detection applications. And along with that, they are also energy sources in terms of the photovoltaic sense with large open circuit voltage and short circuit current. So these devices are custom made to fulfill certain applications. But this field of 2D materials is quite nascent, and a lot of research has to be carried out to have this implementation in the industrial sense. Moving on to the important aspect of photonics during this particular COVID-19 situation. What has photonics enabled in this situation are the following. We all know about the infrared thermography, which is used to screen people, and it's a non-contact method, and it makes use of these IR sensors. In addition, the molecular diagnosis, which involves testing, is carried out using this RT real-time PCR technique, which makes use of these narrowband visible laser diodes, and a lot of non-invasive biosensor technology is under development, which makes use of these photonic sensors. In addition to this, we know that the the damage to the patient's lungs during coronavirus is monitored using the CT scans, which also makes use of photonic technology. In addition to that, pulse oximeters are also used to measure the oxygen level in blood, about which I had mentioned previously. In addition to all the testing, it is also required to detect the presence of antibodies in the body in relation to the SARS-CoV-2 virus. And that is done using this method called ELISA, which also involves multispectral imaging. In application towards vaccines and sterilization, photonics has been successful in these UV-based surface sterilization, which IIT Bombay has also been able to make successfully. So overall, photonics has an important role to play in dealing with the COVID-19 pandemic. To summarize, the roadmap of electronics and photonics looks like this. From early electronics to the electronic integrated circuits that we use commonly, it went through vacuum tubes and the transistors, and the improvement in a lot of scientific technologies led to this development. Similarly, from geometrical optics to lasers and optical fibers to nanoscale photonic integrated circuits, which we are trying to explore currently, we have also seen a growth in the photonic sector, which is set to increase even more because of all the applications that photonics enables. Thank you for your attention. And I'll open it for questions.
I think that was a wonderful talk and it was really informative. It was a very informative introduction to photonics. So participants, in case of any question answers, please raise your hand. I can unmute you. Okay, so I don't see any questions. Okay, we have one question. Yeah, you can go ahead.
Is there a question about femtosecond lasers?
Yes, I think. So you can speak out. You are unmuted now.
Okay. Okay, femtosecond lasers are something that okay, so femtosecond lasers come under pulsed lasers. So not all lasers that we see or employ in commonly are steady state or continuous wave lasers. Some of them are pulse lasers, especially the lasers which work at very high frequencies. So the frequency at which the laser operates is also different. And regarding the applicability about applicability in quantum computing, where regarding quantum computing, I was talking about the single photon emitters, in which the polarization of the light can be synonymous to the qubit, and based on that, a lot of gates can be actually performed. The quantum gates can be actually performed. And the next question is about nanoelectronics in IC. Yes, yes, yes. The silicon dielectric constant can cause crosstalk when the size is reduced. Yes, that's true. And it's also, this field is under research, and uh, so I didn't understand the question. The relevance of optical lattices. Yeah, optical lattices, if I understand correctly, are you talking about the metamaterials which can be used for? Yeah, so the optical lattices.
Okay, Deepali has got a question, so you can go
Yeah,
ahead.
yeah. I would like to ask, like silicon is having the dielectric constant of 4. When you are reducing the size, the crosstalk between the signal will be very high. So, what other possibilities of using any other material instead of silicon?
The entire purpose of using silicon is because the entire electronics is based on silicon, and it would be a direction of research of integrating the optical components, which are typically in non-silicon field, to silicon. So it's a current research topic, and people have proposed a lot of different materials. So material science research towards this aspect is also important, and you can go ahead and read about the latest materials that people have come up with to reduce the crosstalk.
Okay. I'm working on this porous silicon compounds, but the thing is, when the dispersion thing is there, so it is not very well easily dispersed in any kind of metric. So that is what the thing is like. Still, nanoelectronics is preferring silicon instead of the compounds which can reduce the dielectric constant other than silicon.
Yeah, that's because as I mentioned, that the focus has been to incorporate materials into the silicon CMOS based technology, so that it enables like a wholesome approach in which you can have light signals as well as electronic signals working in the same chip. So that has been the that is the ideal situation which is the goal of silicon photonics. And all these issues that you mentioned are problems which are being trying to which are being solved by researchers.
Yeah, correct. Okay, thank you.
Abin, we have one question. We'll take one last question from Debaditya.
Sure.
So you can speak out, Debaditya. Okay.
Yesterday, I actually found some material on optogenetics and how they've been using optical fibers to stimulate neurons in the brain. So, do you have any idea about the field?
I'm sorry, optogenetics is also quite new to me, and I don't have much idea about it.
Okay. Sorry. So there's one other question. Meenakshi has been asking questions constantly. So Meenakshi, you can go ahead.
Yeah, done.
Hello. Okay. So Abin, I think we can close the question answer session. So thank you very much,
Okay.
Abin. That was a great talk and
Thank you.
great Q&A session.